In section 10.2, we're back to doing hypothesis testing based on the population and sample means. However, in this section, we're now dealing with two means and comparing them at the same time instead of doing hypothesis testing based on a single mean. Now, those two means need to come from independent samples. So what's an independent sample? We say that two sampling distributions are independent when there is no relationship whatsoever between specific values of the two distributions. Now let's not confuse this. This does not mean that we're comparing two very different, totally unrelated data sets. It's usually a comparison of one group versus another group where there's a strong similarity. A control group and an experimental group, for example. But there is independence. It's not as if we're saying length of somebody's left foot as opposed to their right foot, because those would be dependent samples. So here is effectively the problem that we're going to come back and you're going to come back and solve at the end of this video. To study the effectiveness of two teaching methods, students are randomly divided into two classes, each taught by a different method. At the end of the course, a final exam is given to all students, and the mean score from Class A is compared to the mean score of Class B. And we can use that to make reasoned conclusions about the effectiveness of the one method versus the other. But we'll come back to that later. First, we have some theoreming to do here, since we are working with working with the comparison of two distributions and two sample means, and two population means for that matter. We have two distributions. Instead of calling them x and x, which would be confusing, we're going to call them x1 and x2. And we'll set up x1, we'll define x1 as having a normal distribution, or, according to central limit theorem, if we're letting the sample size be sufficiently large. x1 has a mean of mu1 and a standard deviation of sigma 1. And x2, again, normally distributed, or we have a large enough sample size where the mean is mu2 and the standard deviation is sigma 2. If we take independent random samples from each distribution, and they do not need to necessarily be the same size, but they should be pretty close. Don't do 10 and 50. If you have 35 and 37, that's not going to be a problem. So we'll set the we'll sample size n. Take a sample of size n1 from the first distribution, and we'll take a sample of size n2 from the second distribution, and we will define this variable. And yeah, we're going to call this one variable, even though you see a minus sign in there. The variable that we are interested in here is x1 bar minus x2 bar. And we have some things that we need to say about that and what that's going to look like. This variable has a normal distribution. If x1 is normally distributed or sufficiently large, the distribution x1 bar is normally distributed, and the same thing would apply similarly for x2. So x1 bar is normally distributed, x2 bar is normally distributed, and so their difference is normally distributed. The mean of this distribution is mu1 minus mu2. Standard deviation, well, that's the part where we have to talk about what this formula is saying. It looks a lot more foreboding than it really is. The standard deviation is defined as the sum of sigma 1 squared. So we know what the standard deviation is from the first sample, and we know how big that sample is. So we'll take the standard deviation from the first sample, square it, and divide by the size of the first sample. And then we'll go do the same thing with the second sample. We'll take the standard deviation and square it and divide by the size of the sample. Add them together and take the square root. So what do we put for the null hypothesis? Well, you've got two choices. It really doesn't matter which one you use. They are equivalent statements. You could say that the null hypothesis is that mu1 minus mu2 is equal to 0. Or using a little bit of algebraic manipulation, you could say that mu1 and mu2 are equal to each other. Go ahead and use either one. It doesn't matter. They mean exactly the same thing. Now, yeah, this also means that the alternate hypotheses are going to have two variations that we could have. There's still three flavors for the alternate hypothesis. One to give us a left-tailed test, one to give us a right-tailed test, and one to give us a two-tailed test. And you can write the alternate hypothesis in whichever of the two ways interests you. You can write it as a difference of mu1 and mu2 being less than, greater than, or not equal to 0. Or you can write it in a straight up comparison of the two, so that mu1 is less than mu2, or that it's greater than mu2, or that it's not equal to mu2. For each of those lines, it doesn't matter whether which of the you say. You could say mu1 minus mu2 is less than 0 for a left-tailed test, or you could say that mu1 is less than mu2 for the left-tailed test. They mean the same thing. Similarly for the right-tailed test, similarly for the two-tailed test. The critical values that we are interested in here, since we are assuming a normal distribution or a large enough sample, we get to use z sub 0. So here are those critical values one more time. At a 5% level of significance for the left-tailed test, z sub 0 is negative 1.645. For a right-tailed test, it's positive 1.645. And for a two-tailed test, it's plus or minus 1.96, numbers we've already been working with. For a 1% level of significance, the one-tailed tests have z sub 0 of negative or positive 2.33, and for a two-tailed test, plus or minus 2.58. To get the z-score, we've got a whole bunch of things to put in. First, we have that variable that we talked about before, x1 bar minus x2 bar. We want to subtract from that the difference between the means. But we're always assuming in these problems, and this isn't necessarily true in all statistics problems of this type, but for our purposes, we're always assuming that mu1 and mu2 are equal to each other. And so ultimately, this whole part of the numerator goes away. And so whatever x1 bar minus x2 bar is, there's your numerator, all by its lonesome. And the denominator is that standard deviation that we talked about before, square root of sigma 1 squared over n1 plus sigma 2 squared over n2. The good news is hypothesis testing is working just the way that you've become familiar with. So all these times that I talk about multiple flavors of, multiple flavors of the same brand of ice cream, that's what we're doing here. We're going from the vanilla to the chocolate to the strawberry to the cookies and cream to whatever flavor you wish. They're all different flavors of the same idea. So the hypothesis testing will work pretty much the same way we're used to. Here's our first example. A consumer group is testing camp stoves. To test the heating capacity of a stove, they measure the time required to bring 2 quarts of water from 50 degrees Fahrenheit to boiling at sea level. None of those numbers are really all that critical to us here, so we'll duck those. They're all decoy information. 2 competing models are under consideration. 36 stoves of each model were tested, and the following results were obtained. For model number 1, we had a sample mean of 11.4 minutes with a standard deviation of 2.5 minutes. And then for the second model, a mean time of 9.9 minutes, and a standard deviation of 3 minutes. And the question that we are asked is there any difference? So you have probably realized by now that the fact that we're not being asked to explicitly compare Model 1 to Model 2 as far as 1 is better than 2 or 2 is better than 1, the fact that that question is not being asked, the fact that the question is there any difference between them, should tell you loud and clear the alternate hypothesis is that mu1 is not equal to mu2. The null hypothesis is that they are equal. The alternate hypothesis is that they are not. Since this is a not equal to, this is a two-tailed test with alpha double prime being 0.05. As a result of that, we can say that the critical values of z sub 0 that we're interested in are positive and negative 1.96. That's what we need to compare with. So when we go and find the z-score in a moment, if we get a z-score that is bigger than 1.96, if z is greater than positive 1.96, or z ends up being less than negative 1.96, in those cases, we'll reject the null hypothesis. And if we can't do that, if we sit somewhere in the middle, then we will fail to reject the null hypothesis. Well, as it turns out, that z-score is 2.30. The difference between the sample means, 11.4 minus 9.9, is 1.5. We're assuming no difference between mu1 and mu2, so that's why we're subtracting 0 at the end of the numerator. The denominator, plug in the values for sigma and n that we have. We sampled 36 of each type. The first model, Model 1, had a standard deviation of 2.5, and the second model had a standard deviation of 3.0. So that's where all those numbers are coming from. We plug them all in, we get 2.30. When you compare that with the critical values, well, first off, we'll leave the negative 1 behind. We know that 2.3 is not less than a negative number. The important part is that 2.30 is greater than positive 1.96. And because of that, we reject the null hypothesis. We ended up further out to the right than that positive critical value, that boundary line. So we will reject the null hypothesis and say that there is enough evidence to conclude that these stoves do not bring water to boil in the same amount of time. Specifically, that Model 2 is doing it faster. So, as I promised / threatened, the second problem is yours, but we'll get started on it together. A teacher wishes to compare the effectiveness of two teaching methods. Students are randomly divided into two groups. They teach the first group by method 1, the second group gets taught by method 2. At the end of the course, a comprehensive exam is given. The first group consists of 49 students with a mean score of 74.8 and a standard deviation of 14. The second group has 50 students with a mean score of 81.3 and a standard deviation of 15 points. The teacher claims that the second method will increase the mean score on the comprehensive exam. Is this claim justified at a 5% level of significance? So I'm going to leave it at that. You've got some questions to answer on Edpuzzle, and we'll be back to go through this in a moment. First off, let's set our hypotheses. The null hypothesis is, as always, that mu1 and mu2 are equal to each other, that there is no difference between them. The alternate hypothesis is that mu2 is better that we are stating that the first group performs worse than the second group. That's why it's mu1 is less than mu2. That is that it's a left-tailed test. At a 5% level of significance, the critical value we are interested in is negative 1.645. So if we can get our z-score lower than negative 1.645, we have a winner. We'll reject the null hypothesis. Go to the z-score calculation. The difference between the x bars is 74.8 minus 81.3. And the difference of the means, the population means the mu's, is 0, as we've talked about before. The denominator is square root of 14 squared over 49 plus 15 squared over 50. Put that in the calculator, and you get a z-score of negative 2.23. Not only is that lower than negative 1.645, it's a lot lower. And so we will say with some pretty strong confidence here that method 2 is indeed better than method 1. In other words, method 2 is going to give you better exam scores. Here are some problems for you to work on.